Ladies and gentlemen, please welcome to the stage the Honorable Paul Dabbar, Deputy Secretary of Commerce.
All right. Hello, everyone. It's bright up here. So I wanted to go through a little bit of the history and how we kind of got to where we're at and where we're now focused on. Many people don't understand the history of AI and science and the development of the current hardware and software stack. And I think it's important for everyone to kind of at least understand where that came from as we think about where do we go in the future. It wasn't that long ago that the GPU had never been used for supercomputing. It was still an idea that Jensen and NVIDIA had been thinking about. Does anyone know who the first real user of the GPU was for a big machine, not just a test machine? Anyone know that? Oak Ridge National Lab, whoever said that. And so it was only about 2017, 16, when the first use of the GPU in a heterogeneous architecture along with CPUs and the use of that to build the software architecture to have that heterogeneous architecture was built with a computer called Titan at Oak Ridge National Lab. I used to always joke, like, we had really bad PR at DOE, at National Labs, about what we did, but at least one person, right, in this room knows that. I think, as many of you know, I was Undersecretary for Science, so I had the honor of running what used to be called the Manhattan Project. And amongst the 6 major offices was the Office of Advanced Supercomputing. And the national labs in DOE have been at the forefront of the next #1 computer, or at least trying to do so, since the Cray 1. And we had lost our leadership, according to the 500 list, the supercomputing 500 list, to China. And the department and Oak Ridge decided to roll the dice on something new, and that came about with Titan. Under President Trump's leadership, they decided to take that architecture, that first kind of use, and to regain U.S. leadership in supercomputing. And so during President Trump's first term, he led the way to Summit. Summit was the first big computer that was #1 in the world using GPU and CPU architecture. I was there at the event. It was a great opportunity, and the president didn't stop. As many of you know, he then signed kind of 2 big tech bills, one the AI bill, and one the National Quantum Initiative Act. And the combination of those two really pushed both forward. I won't talk too much about quantum here today, but he did pass the AI bill amongst that, which then accelerated across the board from that first machine to, frankly, a lot of what we're seeing here today. When I was Undersecretary, we started something called the Exascale Computing Program, which was basically take what we had done with Summit and to significantly scale it even farther. And ultimately, we bid out and procured 3 computers. So during, from the president's leadership and footprint, depending on your operating metric, he triggered 4 #1 supercomputers in the world. This didn't just happen, and everyone kind of looks at AI today and go like, it's almost like it's always been here. No, this was only 2017, 18, 19, right, and then the rollout of Exascale over the last few years that we started building and laying out. Another thing that's kind of very important for the history of what we've done here, and this directly gets to the AI for science topic, is concurrently with building a machine, is building the application stack, right? You're not building these machines in isolation of what you want to go use it for. And the first use case for AI running on this hardware and software operating stack was for science. It became very obvious to us that the first use case, like a lot of supercomputing, was in the science space. That's why the #1 supercomputer in the world was perennially at the national labs, because there was a use case associated with it, and that was scientific discovery. For those of you who may not know how the structure of Office of Science and whatnot, there's a program office in what's called basic energy, which is including materials and chemistry, big funders of materials and chemistry. Fusion's in the list. A lot of the high-end physics, so high-energy physics, nuclear physics, biology. Most people didn't realize that I had a bit of a footprint in biology through the national labs. We actually started the Human Genome Project and was the at Berkeley for CRISPR. And all these things could have been used, and in the later stages of what I just described, was being used by AI to help drive that innovation. Another piece of history here, which I still find quite funny, was when COVID hit and we were trying to figure out about different treatments that could hit that. We had, for various different reasons, had ramped up the prospects of using our biology discovery stack at not only at Oak Ridge, but at a couple of other of the national labs to start thinking about biotopics. And when the COVID hit, we were immediately able to shift to the analysis of the SARS and MERS genomic sequences, comparing the proteins associated with it. I can't remember the exact numbers, but I think COVID-19 was kind of 90% of one and 93% equivalent of the sequence of the other. It was extremely close. There was a lot of work done on SARS and MERS as a result, specifically looking into individual proteins and potential therapeutics that could be used against that. We were also, we quickly got the genomic sequence associated with COVID-19, compare that to all the scientific work that had been done on the individual proteins associated with the previous similar viruses. Also quickly figured out which proteins had human analogs and ones that did not, i.e. those are side effect prospects. And in about 3 weeks, we figured out a stack of about 10 options for COVID-19 that would have the highest probability of going after certain proteins, hopefully not having ones on human analogs. And that took 3 weeks. And there's a reason why solutions for drugs are now like that one, are happening in 9 months versus the previous all-time high, speedy drug discovery of about 4 years. And the primary reason isn't that they figured out how to do trials faster. It's because when they got to the trial, they had a much, much higher probability of actually having something that was successful. In April 2020, the nominee for Undersecretary for Science, Dario Gil, and I did an interview with the Wall Street Journal. And this is in the middle of all this. And we did an interview where we said, new AI driven by heterogeneous architecture, GPU, CPU machines, are going to be able to accelerate this and every other discovery in the biology space. No one paid attention to us. It was in the Wall Street Journal. The two of us, the head CTO of IBM, helped build these machines, and myself as Undersecretary for Science, were saying, this is the future. And we got up, and afterwards, there was no questions. No one reached out to us. It was the Wall Street Journal. I'm glad that they actually, highlighted it. But no one paid attention. And we had this kind of lamenting conversation of, no one's paying attention. Let's jump forward to today. Everyone's brilliant, right? Everyone knows AI. Everyone it's obvious. It's always been around. But that's a little bit of the history. It was really not a long time ago. And I think it's very important to kind of understand a little bit of that history and to have a little bit of humility about what we all assume is the answer here today. and realize that it really wasn't very long ago that no one was, in 2020, no one was paying attention, right, to this topic. So jumping forward, we also developed, with the president's leadership, something called AI for Science. And the exact same month that the federal government side, president's leadership on the AI bill and whatnot, and AI for Science, was to develop a suite of AI products for scientific discovery. Eric Schmidt also announced a session, literally the same month. I was reading about it, and he was like, so Eric Schmidt's going to be starting an AI for Science effort. I forget what year it was, maybe 2019. It was like a summertime, if I remember correctly. And I was like, well, that's interesting. We're doing the same thing. And so there was that kind of parallel kind of thought leadership effort, which became the association here today, organizing this, and the president's leadership on this and the efforts in the federal system and driving that forward. Jumping forward to today, obviously there's, I have to admit, I'm not 100% for certain what's public at the moment, but obviously an expected announcement on a number of things. I won't comment to that. I'll let that move forward. But you will see a lot of leadership across the federal spectrum, led by the president. A number of things that you're saying they're jumping even farther forward than he did the first time. And Secretary Lutnick at the Commerce Department, where a lot of the AI efforts are focused on. Let me hit on a couple of those. Obviously, the big one is CHIPS and Science Act. I think we have someone who helped write the bill previously. There's a bucket associated with that. So when you think about chips and AI, it's hard to kind of, especially in today, to kind of separate the two, especially at the higher end design and higher end of the fabrication side. So there's a huge effort of which under the Secretary that we've taken what was kind of there not that long ago, and depending on the project and the company, we've literally tripled. So there is, once again, not knowing everything that's public, but if you look at what's going on in Arizona, what was going on last year, depending on who you look at in the company, it's tripled. The performance of what they're doing on fab and fab performance and productivity and yield rate was so strong, they decided to triple down. So TSMC went from $65 billion and one fab to, once again, I can't remember how much is public, but 165 and 3. I would say there's tremendous momentum behind the scenes in that sort of realm of what we're seeing in terms of that support. So the high-end fabrication. Also within the CHIPS Act, there is a next-generation CHIPS R&D effort. And so that's a whole area that the Secretary is spending significant amount of time on how to really look to the horizon. Not to look at doing something incremental, but looking on the horizon. If there's one thing about about President's leadership and Secretary Lutnick's leadership, is not about tweaking and and doing incremental work. It's about what's the horizon and what we're going to go take. So there's a lot of work associated with that. And not only that, when you start thinking about AI and AI for science and kind of what I would call the application of science, I talked about the application of science for biology. It's obviously incredibly easy to think about, and once again, now it's like common knowledge. There's even startups using AI for discovery on various different aspects, but in chemistry, right, in materials, things like that. Fusion containment design and operations. Obviously, biology, I already talked about that. So while a lot of people, focus on large language models and ChatGPT and whatnot, which is incredibly important, but once again, just like the history of supercomputing, the history of how these things have been developed, including AI algorithms, science is the most obvious first case applications that can have the biggest impact. On the biggest impact topic, I do want to talk about economics and productivity. If you take a look at, if you just kind of go to the simple equations of economic growth in general is population growth plus productivity growth. And productivity growth is, has many different aspects to it, including, like manufacturing capacity and whatnot. But a lot of it, if you look at a lot of the literature, this sort of technology development is about half of productivity development growth. So if you think about U.S. economic growth at a lower level, kind of current-ish last few years, 2 to 3% economic growth, which is, by the way, good compared to some other countries in the world, but still not as aspirational as what it could be. So if you look at that, you might have 1% population growth and 2% productivity growth, or somewhere around there, kind of plus or minus. So if you think about how do you drive productivity, and that 50% of it, according to most studies, is driven by this technology innovation. If we could drive down the cost of innovation, if we could speed up innovation, that shows up into that second number, and it leads to economic growth associated with the country. There is great opportunity here from AI to take that second number, to take that productivity growth, and to accelerate it, to increase it at the simplest levels. So moving that from 2% to 3%, right, that 50%, if we can take that and double the productivity growth associated with technology development, of which AI and science develop of new technologies, that whole kind of umbrella, it's completely doable. And the president's highly focused on getting growth up, and what you're seeing here on announcements, what's going on, ultimately ends up to that for the American people and for American leadership in the world. So if we can move from 2.5% or so economic growth to 4%, how do we do that? That productivity growth is in part building new manufacturing and so on, but part of it is this conference, right? This topic, and so it can be done. I've just went through the history. The opportunity set and where the president's going and where the secretary is going is going to be quite visible here in a few minutes or so. And it has real impact to the American people and American leadership in the world. So that's kind of the summary, I think, of where we're going. A lot of us who are working for the president, who are working for the secretary, were around last time. I think I'm a somewhat familiar face to a lot of people here in this room. Director Kratsios is somewhat familiar. You're seeing people at DOE that are somewhat familiar. Lab Complex, labs at NIST. And so the vision about taking the next hill and the big ideas, not small ideas, big ideas around AI applications, semiconductor manufacturing, design, and what I'm not talking about today, quantum. Those kind of what I call the big three is absolutely going to be driven harder and faster, just as the president did the first time. So thank you, everyone. I'm glad for everyone's interest in this topic. It's super important.
Now we are